So in this lesson, I'm going to be discussing electromagnetic radiation. Now, you experience electromagnetic radiation in your everyday lives. When you listen to the radio, when you use the microwave to heat up your food, when you go out and get sunburns in the sun, when you break your leg and you need x-rays. So this diagram right here shows electromagnetic radiation. And there are a couple of quick definitions that I need to give you. Okay? The first one, notice you've got the tops of the peaks of the wave, and then you've got the bottom parts of the wave. So the top part of this peak of electromagnetic radiation is called the crest, while the bottom part is called the trough. So really quickly, before I get into comparing wavelength, I've got to first define what that wavelength is. So wavelength is the distance between two crests or two troughs. So let me show you what that looks like. So when I look at this electromagnetic radiation right here, the distance between this crest and this crest, that is your wavelength, okay? So a couple of quick things. The symbol we use to represent wavelength is this lambda symbol, okay? And the units for wavelength are going to be in meters because units for length are often meters, okay? Or your wavelength could be the distance between two troughs, so the distance between those guys, okay? Notice, just in general, when I start here on my left-hand side with radio waves for my type of electromagnetic radiation, the wavelength is very long. When you get all the way to gamma rays, the wavelength is much shorter, right? The distance between the crests or the distance between the troughs decreases significantly, okay? So just relative size-wise, the wavelength for radio waves is comparable to the height of buildings. Okay? When you get to microwaves, we're getting smaller than the size of humans, but larger than the size of butterflies for wavelength. Okay? And then when we get all the way down to gamma rays, which have very short wavelengths, we're talking about the size of an atomic nuclei. So much, much smaller. Okay? So that's wavelength. Let's talk about one other characteristic of electromagnetic radiation that we're going to talk about today, which is frequency. Now, frequency is the number of times a crest passes a point in 1 second. So let me write that out and then explain. So let's look at what that looks like. So if I give you a specific point here, what I'm saying is your frequency is how many times a crest is going to pass through that point in just 1 second. Okay? The symbol to represent frequency is the symbol here. It's like a check mark. That's called mu. And since frequency is not saying the amount of time it takes, but instead how many crests pass per second, my units are going to be per second, which is going to be 1 over seconds, or just seconds to the -1. And so that represents, this is not actually time, this is saying how many times per second, or another unit for frequency is hertz. Okay, so let's quickly relate frequency with wavelength. Well, if you notice, when I have a long wavelength like I have right here, the number of times a crest is going to pass through that point is going to be much lower than if I have a shorter wavelength. More crests will pass through a point the shorter your wavelength because they're closer together, which makes sense. So what I'm saying is that the higher your wavelength, the lower your frequency. Or the shorter your wavelength, the higher your frequency. So they are, when one goes up, the other goes down. That relationship is an inverse relationship. So we're going to see how wavelength and frequency relate with this simulation really quickly. So notice here, the wavelength is so long for radio waves that it actually just looks like a straight line. It's simply because the computer screen can't show a whole wave yet because the wavelength is so long. Notice as I move down, I still can't see these waves, right? The wavelength is too long, but notice as my wavelength is decreasing, right? I'm going to TV, to the mobile phone, to your Wi-Fi. Notice what's happening with your frequency. Let me go back to the top and show you again, okay? Notice how my frequency is increasing as my wavelength decreases, right? Frequency's on top, wavelength's on bottom. They're inversely related, okay? Still can't see the wave. Look at all of these different uses of electromagnetic radiation in your everyday lives. We're going to keep going down, keep going down. Notice, oh, I'm going to start to see a wave because I'm decreasing enough. All right. Okay. Now that's for infrared cameras. Okay. Your remote controller, notice your wavelengths are now much shorter, so we can actually see full waves. So this is what you use for your remote controller. Okay, the wavelength is between 940, 980 nanometers. Okay, let's decrease the wavelength even more. We're going to get into your visible light. These are colors you can see. So notice at the very top, so the longest wavelength for light is red, orange, then it's hard to do, orange, then green, then turquoisey, then blue, then purple. So purple, notice, has the shortest wavelength, the highest frequency. Okay, and then we're going to go on. So this is when you tan. So notice the wavelength for UV is shorter than the wavelength for visible light. Okay, I'm going to decrease even more. Okay, notice wavelength's getting shorter and shorter, frequency is greater and greater. Okay, this is X-rays. Okay, so in order for us to be able to see inside your body, you need much shorter wavelengths and higher frequency. And then we're going to get all the way down. Okay, and then that's as far as the simulation goes. So notice how close together the wavelengths are down here. Notice you have a very short wavelength and a high frequency as you move up. Notice the distance between the waves increases. Okay, it increases even more as your frequency decreases until the simulation, once we get right up to about here, we no longer can detect it because the wavelength is so long. Okay, so another valuable tool that we want to be able to have is to actually mathematically relate wavelength and frequency. So the formula I'm going to use is the following. C equals lambda nu. So let's redefine all of my variables. So remember, that is my wavelength. Okay, and my units are going to be in meters. This is my frequency. And my units are either going to be in seconds to the -1 or hertz. Okay, and my last variable here is c, which is my speed of light. And that is 3.00 times 10 to the 8th meters per second. And so this is really important to note. When I'm using this formula, since my units for the speed of light are meters per second, my units for wavelength have to be in meters and they have to be in seconds to the -1 or hertz. If they're not, you first have to convert into meters or seconds to the -1 before you can use this formula. Okay, so let's actually do some practice problems. So example 1, what is the wavelength in meters if the frequency is 1 times 10 to the 14th? So I'm going to write out my formula. Okay, my speed of light I can plug in, it's the same always, 3.00 times 10 to the 8th. Okay, it's asking for my wavelength. So I'm going to put lambda, okay, times my frequency, which is 1 times 10 to the 14th. Okay? So this is where it's important for you to make sure that you're paying attention. I need to solve for lambda, so I'm going to divide both sides by 1 times 10 to the 14th. Okay, and this is where students often make an error. When you're plugging this into your calculator, you need to make sure you'll take 3 times 10 to the 8th. When you divide, because there's a multiplication symbol here in the denominator, you need to make sure to put this entire value in parentheses. Otherwise, what your calculator will do, and it's not its fault, it's yours, it'll take 3 times 10 to the 8th, it'll divide by 1, and then it'll multiply by 14. So you'll end up with 3 times 10 to the 22nd, which is not what we want. So you need to clearly tell your calculator, hey, I want you to divide by this entire value. So to show this on the calculator, I'm going to do 3 times 10 to the 8th. Okay, notice it's up right now. I'm up in the exponent, so I've got to scoot over. And I'm going to divide by, and I'm going to put this in parentheses, 1 times 10 raised to the 14th. Okay, make sure to scoot over again and close your parentheses. Okay, so that's my value. That is in standard notation. Now, if you don't want your calculator to be writing in standard notation, you always want it to be in scientific notation. All calculators are different, but for this one, if you hit mode, notice how it says norm, sci, engineer. So if you hit sci, what that'll do, and then I'm going to second quit out of this, if I hit enter, now it gives it to me in scientific notation. Okay, so when you solve for this, the value that I get is 3 times 10 to the negative 6. Now, the reason why I put 3, notice I have, for 3.00, I have 1, 2, 3 sig figs. For 1 times 10 to the 14th, I've got 1 sig fig, so my final answer should have 1 sig fig. My units are going to be in meters, and that is my answer. Okay, let's do another practice problem. All right, it tells me the blue color of the sky results from the scattering of sunlight by air molecules. The blue light has a frequency of about 7.5 times 10 to the 14th hertz. Calculate the wavelength in nanometers. So the first thing I'm going to do is I'm going to write out my formula. C equals lambda nu. Okay. The speed of light is 3.00 times 10 to the 8th. Okay. I'm solving for my wavelength, so I'm going to put lambda there. And my frequency is given to me, and it's in hertz already, which is what I want it to be in to use this formula. So I'm good to go there. Okay, so now I'm going to divide both sides by 7.5 times 10 to the 14th. Okay, remember when you are dividing in your calculator to put 7.5 times 10 to the 14th in parentheses. And so what I end up getting for my wavelength is 4 times 10 to the negative 7th meters. Or you could have also gotten, in standard notation, it's the same value, this. Okay, notice right now I have only 1 sig fig, but I'm not done with the problem, so I'm going to just keep going. Okay, so I'm going to take my 4 times 10 to the negative 7th meters. Notice I don't want to be in meters, I want to be in nanometers. So what I'm going to do is I'm going to get out of meters by putting that unit on bottom, and I'm going to get into nanometers. So remember, for every 1 nanometer, you have 10 to the negative 9th meters. So I'm going to take 4 times 10 to the negative 7th, and I'm going to divide by 10 to the negative 9th, and what I end up getting in nanometers is 400 nanometers. Well, it would be awesome if I could call it a day and be done. However, I need to figure out sig figs. Okay? Well, 3.00 has 3 sig figs. 7.5 has 2. So this value, my 400 nanometers, needs to have 2 significant figures. The issue is if I put a decimal after the 0 for 400, that would give me 3 sig figs. And without it, I only have 1. So in this case, that tells me I'm going to have to put this into scientific notation in order to get 2 sig figs. So what I'm going to do is I'm going to move my decimal place 2 places to the left. So that becomes 4 times 10 to the second nanometers. And now, because I'm in scientific notation, I can manipulate this to get 2 sig figs. So I can put 4.0 times 10 to the second nanometers. And that's my answer. I've got the correct number of sig figs and the correct units. Okay, let's look at the next problem. It asks, what is the frequency in megahertz if the wavelength is 625 nanometers? Okay, so here's my formula again. Now keep in mind, my wavelength right now is in nanometers. I cannot plug in nanometers to this formula. I have to be in meters. So the first thing I need to do is get myself out of nanometers and get myself into meters. Okay, so 1 nanometer is 10 to the negative 9th meters. So when I do that and multiply by 10 to the negative 9th, I get 6.25 times 10 to the negative 7th meters. Okay, that looks great. Now I can plug it into my formula. So 3.00 times 10 to the 8th is my speed of light. That equals my wavelength. My lambda, 6.25 times 10 to the negative 7th. Okay, times nu, which is my frequency. So now to solve this, I'm going to divide both sides by 6.25 times 10 to the negative 7th. And remember, when you're plugging this into your calculator, make sure the 6.25 times 10 to the negative 7th is in parentheses in your calculator. Okay? And so when you solve for your frequency, what I got was, because I want 3 sig figs, 4.80 times 10 to the 14th hertz. Okay? Be awesome if I could be done, but I'm not because it asks for megahertz. So yes, I have to do one more conversion. I'm going to put hertz on bottom, megahertz up top. Okay? 1 megahertz is 10 to the 6th hertz. And those are all values. These are all prefix values that we learned previously. So you can always just go back and check it, or on a quiz or test, I would give you those values. So I'm going to take 4.80 times 10 to the 14th, divide by 10 to the 6th. So the final answer I get is 4.80 times 10 to the 8th, and my units are megahertz. Double checking sig figs quickly. I've got 3 sig figs from 625, and 3.00 has 3 sig figs. So I'm good with sig figs, and I'm good with units.